Okay, we're back at it again tonight. Okay, so today what we're going to do is we're going to talk a little bit about Coulombs law. Now, what is Coulombs law? Really simple. We talked about yesterday when things lose or gain electrons, they become charged. Charged atoms are called ions. And then what happens is if you have two charged objects, they're going to either attract or repel. And we talked about that yesterday too as well. We have two things that are like charges, they're going to repel each other, and we have opposite charges, they're going to attract. Well, if they're going to attract, they're going to move towards each other. A better word than move is accelerate. We always use that term at the beginning of the year. And it turns out if they accelerate, well, according to a guy named Newton, there has to be a force that's causing that. And that's what Coulomb's law is about. Coulomb's law is about the force of attraction or repulsion between two objects. So if we were to look at something like this, and we have an object here, and we have an object here. Let's say that this guy gains electrons. So remember, if it gains electrons, it becomes negatively charged. Let's say this guy lost electrons, this guy becomes positively charged. Now that we have two objects that have opposite charges, they're going to attract to each other. So this object would want to accelerate that way, and this object would want to accelerate that way. These two objects are attracted to each other. They're going to feel a force, and they're going to accelerate towards each other. So what we want to do is we want to find out, how do we determine the force that attracts these two objects? Now, I think most of you should be able to think about this concept. How can I make this force of attraction a little bit stronger? Well, one of the ways is by making this guy a little bit more negative, by giving him more electrons, giving him a bigger charge. Or this guy, by taking more electrons away from him, giving him a bigger charge. So it turns out, if we were to increase the charges of either one of them or both of them, they're going to feel a stronger force of attraction or repulsion towards each other. Oh, so we can talk about charges. Now, the other thing we could talk about that could affect this would be the distance between these two. I think this would be common sense in that if we take these two and bring them really far apart, that force of attraction should decrease. Bring them closer, that force of attraction should increase. Now, Coulomb understands this concept, and he comes up with an equation that governs the attractional force between these two. Now, this should be very similar to an equation we had before. If I look at this, when Coulomb comes up with this concept, that the force, well, we just talked about it, is dependent upon the charges, how many electrons it gained and how many electrons it lost. Now, we have to come up with a symbol for charge. So the symbol we're going to come up with for charge is Q. Now, some books use a small q, some books use a big Q. We'll explain the difference later on. Depends on if it's a big charge or a small charge. I'm going to go ahead with a big letter Q later on. Probably tomorrow or the next day, we're going to talk about the lowercase q. They both mean the same thing, charge. So, well, if we think about it, the more charge, the greater the force. So we talked about it, that should be a direct relationship. And we have to have two charges. So we're going to call that Q1, we're going to call that Q2. Q1 and Q2 is going to be the charges on each one of those objects. Now, we also talked about it's the distance. Well, when the distance goes up, the force goes down. So, that should be an inverse relationship. So we have the direct relationship of those, and we have the inverse relationship of distance. And it turns out that it's distance squared. Now, last but not least, there is a constant here. That constant is called Coulomb's constant. It's just a number we have to add in there in order to get the correct answer. We'll talk a little more about that constant later on. But if we look at F is equal to K, Q1, Q2 over distance squared. Oh, now, what equation does that kind of look like? Well, if you go back to the force due to gravity, that's big G, mass 1, mass 2 over distance squared. So sure enough, that looks very similar to it. We have the two masses and a distance squared, and G was a constant. So it turns out this equation is very similar to this equation. So the force of attraction between two objects of mass, let's say this pen and the earth, I drop it, there's an attraction force. We talked, it was dependent upon the two masses and depending on how far it is apart. Well, same thing goes for this force, Coulomb's law, the force of attraction between two charged objects or repulsion. It turns out that it's Q1, Q2, again, Q stands for charges, okay? D is the distance and K is a constant. Now, if you remember a couple of things, when we talked about this one, that force of attraction between two objects of mass, turns out that any two objects that have mass are attracted to each other. We talked about that when we talked about the universal law of gravitation. Well, it turns out, though, this force is a very weak force. The only time we ever noticed this force is when one of the objects was really massive, like planet size. So this was a very weak force. And in order for that to be a weak force, this G was a very, very small number, 6.67 tiny, very small number. Now, this chapter, it turns out that this force of attraction or repulsion between two objects actually turns out to be a very strong force. So this is considered a very strong force. So there are some differences between universal law of gravitation and Coulomb's law, in that this was considered a weak force in nature. Electrostatics is considered a very strong force in nature. Now, if that's the case, this G was a very small number. Turns out that this K is a pretty big number. Now, what is that one? Again, this is something you can put on the back of your card, so you don't ever have to memorize this one. It turns out that K has a value of 9.0 times 10 to the 9th newtons meters squared over coulombs squared. So it's a very large number. Okay? To the 9th is, to the 6th is a million, to the 9th is a billion. So 9 billion, okay, newtons meters squared over coulombs squared. We'll explain those units later on, but it's a pretty big number. And since this is a pretty big number, that means this force is going to be a strong force in nature. Guaranteed to be a question on a quiz, guaranteed to be a question on a test, okay? So we do have to know that this is a strong force, and there. Now, again, it's very similar, but there are definitely some differences. As an example, this was only an attractional force. Gravity, the objects, two masses were always attracted to each other. They never repelled each other. So on this one, remember this force can be either attraction or repulsion depending on those charges. Again, from yesterday, if two charges are positive and positive like charges, they're going to repel each other. If one's a positive and negative, they're going to attract each other. So this one is a strong force, and it can be attractive or repulsive. So it turns out we can have either one, an attractional force or repulsion force, depending upon what those two charges are. Now, without going into any math yet, let's talk about a couple of things. Again, exactly what we did with this equation. Let me erase that. Let me erase this, and I'm just going to keep this equation up here for now. So now, if we look at this one, this just tells us that if we have an object here, plus we have an object here minus, and this is the distance between them, that they're going to be attracted. That K is a constant. We need to know the charge of this one. Remember, the charge is really just how many electrons it gained or how many electrons it lost. We'll explain that one later on. This one is how many electrons it gained or how many electrons it lost, and then the distance between the two. Now, what happens if we were to double this charge, just on this guy? So if this guy was to become twice the amount of charge, what would happen to the overall force of attraction and repulsion? Well, in this case, since it's two opposite charges that be attracting each other, this one's attracted that way, this one's attracted that way. Well, if I was to double one of those charges, again, I put a 2 on this side. Well, if I multiplied this side by 2, guess what? This side needs to be multiplied by 2. Remember mathematic rules, and that means the force would be twice as strong. Now, what happens if I was to double both of these? Well, if I was to double this charge and double this charge, I'm multiplying this side by 2, and again, another by 2. So really, I'm multiplying this side. 2 times 2 is 4. So that means this force would be 4 times as strong. Again, we went over these same types of relationships when we talked about the universal law of gravitation. These, again, would be some good ones to know for a test and a quiz. Now, what if I get rid of those and we just go back to our normal plus and our normal minus? What happens if I was to double the distance? Well, now, if they get to be further away, we know this distance and force are inversely related. We know that it's going to get a weaker force. Here's, again, where a lot of people make a mistake. If I double the distance, a lot of people want to say the force goes down by a factor of 2 or 1/2 as much. That's not correct, because the one thing that you're forgetting, that it is distance squared. So if I was to double the distance, I take 2 squared, that becomes 4. Ooh, so 4 now is on the bottom. This would be 1/4 as much. So if this guy doubles, this force becomes 1/4 as much. Now, fractions on the bottom we could talk about. If this is going to be 1/2 the distance, now what do we do? 1/2, again, we still got to square it. We bring it closer, it should go up. Well, if I do this 1/2 squared, I get 1/4 on the bottom. Remember in math, if you have a fraction on the bottom, you can flip it up And it turns out that it would be 4 times as much. It would quadruple the force. And so we can start thinking about those relationships between this. So Coulomb's law is pretty simple. Coulomb's law just says if you have 2 charges, they're going to be either attracted or repelled by each other. And if I know the charges on each one of them, and I know the distance between them, okay, I can now calculate that force. Now, last but not least, and this is an important one, again, we've talked about this before in the universal law of gravitation. Let's say I have one that has a whole bunch of positive charges, and this one only has extra one negative charge. So this has a much bigger charge than this one. Well, which one is going to feel a greater force of attraction? Will this one or this one feel a greater force of attraction? The big misconception is people are like, oh, this one is, or this one is because of the amount of charges it has. If we go back to it, there's only one equation that governs this. And it turns out Newton's third law kind of tells us this. If you remember Newton's third law, for every action, there's an equal but opposite reaction. It turns out this guy is attracted to this guy, and this guy's attracted to this guy with the same force. So it turns out no matter how big this charge is compared to this charge, they're going to have equal forces, equal but opposite forces. Now, if you remember back to Newton's law, which one of these 2 charges would be affected more by that force? The one that has the least mass. The least mass would accelerate the greatest because A is equal to F over M. But again, we can start thinking about the concept. But the big one is when these 2 forces are attracting each other, they're going to have the exact same force acting on them. Whether one's bigger charge or one's smaller charge, they're going to have the exact same force acting on them. So we have that force and we have that force. Same force there. Now, what happens if this was a positive and this is a positive? Same thing, but the forces now would be acting this way, repulsion. So any questions on that? No, didn't think so. Sure, no questions? Okay. Now, let's go ahead with this. Now, what happens if I wanted to do some math with this one? Well, in order to talk a little bit about some math, distance is easy. Like I said, this is going to be a constant. We talked about the constant. Let's talk a little bit about that one. That Q stands for charge, the charge in each atom. The way you charge an atom is by adding or subtracting electrons. We won't go into it about what the charge of one electron is. We'll give you that value and we'll do some calculations with that on a later date. But you got to think about how something gets charged. It's going to get charged by adding an electron or subtracting an electron. We call that quantized. So there's a whole theory of physics about quantum mechanics. It's about how things are quantized. Steps are quantized. I can go up 1 step at a time, go up 2 steps at a time, or if I want to, I go up 3 steps at a time. But in each case, it's always at multiple of 1 step. Well, same thing with charges. Charges, I can make something by adding 1 electron, adding 2 electrons, adding 3 electrons. So that electron is the smallest amount of charge that we can add or subtract. Hence, we call that quantized. The quantized step is the charge of an electron. Now, with that said, we have to come up with a unit for charge. Well, it turns out that the unit for charge is a coulomb. And it is going to be a capital C. Now, why is it a capital C? Because lowercase c, talked about, is already used for speed of light. And so it's going to be a coulomb, and it's a large C. And really, a coulomb just stands for a whole bunch of electrons that were given or a whole bunch of electrons that were taken away. And so a coulomb of charge, or coulomb, is just a measure of how many electrons that were given or how many electrons that were taken. And we'll do some calculations with that tomorrow. Okay? Now, what I want to do is I want to do some calculations with this one today. Now, if I look at this one, Q would be a charge. This is a charge of the distance. Again, this should be really easy. It's going to be nothing more than plug and chug. I'm going to give you 2 charges. I'm going to give you a distance. We know K is a constant. We're going to plug it in. We're going to find out what the force of attraction or repulsion is on them. So now let's do a simple problem like that one. Let's say I have an object right here that's a positive charge and an object right here that's a negative charge. Now I'll give you those charges. Let's say that this guy has a charge of a positive 3.0 times 10 to the minus 6 coulombs. Now that's a very famous charge. It's really called 3.0 microcoulombs. So a lot of times you'll see in books it says 3.0 microcoulombs. Now if you remember, micro is a metric prefix that means 1 over a million or 1 millionth of it. So a lot of times in a book, if you ever see that micro, what we do is we just get rid of the micro. We put in times 10 to the minus 6 there. Now, why is that kind of familiar? If you ever shock, like you scuff your feet and shock somebody, or, you know, especially when it's wintry, and you pull off your, blanket, and you shock somebody with that, turns out that's about a microcoulomb of charge. It's a very common amount of charge. Okay? And so let's say that this is a positive 3.0 times 10 to the minus 6 coulombs. Let's say this one is a minus 2.0 times 10 to the minus 6 coulombs. Now let's just make sure we revisit this one. If this is a positive, a positive means that somewhere along the line it lost a whole bunch of electrons. There's materials that like to lose electrons. There's materials that like to gain electrons. This is a material that liked to lose electrons, and that's why it became a positive charge. Now this one is negative. Well, that was a material that liked to gain a lot of electrons. Notice this is a positive 3 microcoulombs, or times 10 to the minus 6 coulombs. This is a minus 2.0 microcoulombs, or times 10 to the negative 6 coulombs. Notice this is a bigger charge than that one. Okay. Now, let's give you a distance. Let's say that these two are a distance of 2.0 meters apart. So now what I would ask is, what's the force of attraction or repulsion between these two? Well, right off the bat, let's go ahead and just plug numbers in. So I'm going to use this equation. Remember our 3-step process? I'm going to put in K. K is a constant, 9.0 times 10 to the 9th newtons meters squared per coulomb squared. Again, we'll talk about those units in a second. I'm going to now multiply that by a positive 3.0 times 10 to the minus 6 coulombs. I'm going to multiply that by a minus 2.0 times 10 to the minus 6 coulombs. I'm going to divide that by 2.0 meters squared. Don't forget to square that value on the bottom. So again, if I was to put this in my calculator, there, I'm going to go 9.0 second EE to the 9th. I'm going to multiply that by 3.0 second EE to the negative 6th. I'm going to multiply that by 2.0, negative 2.0, second EE to the negative 6th. Enter. And then I'm going to divide that by 2 squared. And if I do that, I come up with a value of about 0.014. I'm just keeping 2 significant digits. Remember, leading zeros are not significant. And now let's look at the units. The coulomb squared cancel out, the meters squared cancel out, so we're left with newtons. Now, it turns out somebody's going to like, Mr. Murphy, you forgot something, and I did. Mathematically, what I forgot is there's a negative sign right there, and that should be negative. Now, in the past, what would a negative sign on a force tell us? Well, a force is a vector quantity, so a negative sign would tell us absolutely a direction. It turns out in this chapter that does not tell us a direction. It turns out that this sign tells us whether it's going to be attraction or repulsion. It turns out in this chapter, if you have a negative sign for the force, it tells us that, in this case, negative, they're going to be an attraction. Okay, if it's a positive sign, think about a positive sign. Positive sign would be positive and a positive charge. A positive and a positive charge would make it positive, or a negative and a negative. Well, negative would make it a positive as well. And it turns out that would be repulsion. Now, why does that tell us that? Well, again, in mathematics, a positive and a negative, opposite charges. You'll always get a negative sign there. That's going to tell us that there was 2 opposite charges, and opposite charges attract. We have 2 like charges, positive, or negative, negative. When we multiply them together, yes, you'll always get a positive. So positive tells us repulsion. And so when I look at this one, these are going to feel forces. Now, if you go ahead, if I wanted to, again, I could draw lines there. These are going to feel 2 forces that way. Now, again, I could ask this question, a very good question, not to mislead you, but which one of these 2 feels a greater charge? Even though they're different charges, it turns out they feel the same force. It will be 0.14 newtons that way and 0.14 newtons that way. That's why that negative sign doesn't give us a direction. It's actually a force acting in both directions. It's pulling that one this way, it's pulling this one this way. They're both going to feel 0.14 newtons. Which one will be affected more? The one that weighs less. It would accelerate faster. A is equal to F over M. Okay? And so we could start thinking about Newton's, or not Newton's, but Coulomb's law. And again, if I look at this one, K is that constant, Q is the 2 charges, and distance is the distance squared. Again, it should be a pretty simple calculation. We're just going to put in two charges and a distance. We know K, and we're going to find out that force of attraction or repulsion. Big things on this one is, again, if it's a negative sign when you finish out, it just tells you that it's a attraction. If it's a positive sign when you finish, it tells you repulsion. And again, I would give you those two charges. Tomorrow, we're going to talk much more about this Coulomb and this Coulomb, in that it tells us really how many electrons were gained and lost. We could actually figure out exactly how many electrons that were gained or how many electrons were lost. Again, remember, charges are because we're gaining or losing electrons, and it's going to be based off of that one charge of one electron. Okay? And so pretty simple, pretty straightforward. Okay. So now, tonight, again, you're going to have another forms. It should be pretty simple. A lot of the questions, the first 4 or 5 questions are just choice. You're going to have one calculation. Again, I'm going to give you two charges. I'm going to give you a distance, and you're going to solve for that force. Again, don't forget that the K value is a constant, and it's right there. Tomorrow, we're going to go ahead and talk a little bit about charge on one electron. We're going to talk about some math with that. Okay? And then we're going to talk about fields. Now, if you wanted to look this in your textbook, this is chapter 16 of our textbook. And we're going to pretty much go chapter 16, chapter 17, and chapter 18, and then we're going to be pretty much done for the year. And again, this would be exactly what we'd cover in a normal year as well. So any questions on that? Matthew Michaels, I see your hand raised up, or are you sleeping? Nope, okay, never mind. Okay, just trying to add some humor there. Matthew, that was for the your bottle that you opened up and it smelled the room up. For those that aren't in the class, he had this bottle that he put his protein drink in, forgot it in his locker for like 2 weeks, took it out, opened it up in our classroom, 7th hour, and did that smell really bad. It was actually kind of funny, but it pretty much disrupted the classroom for at least a good 20 minutes. Because then they decided that he was going to spray cologne in the room, and everybody's gagging on a cologne. So, but anyways, everybody have a great night, and then we'll see you here again tomorrow.